Welcome to this short presentation. My name is Marco Muniz. I'm going to be showing what we have been doing in the EcoRun project. This is work together with Anders, Kim, and Thomas. We are working on the domain of mobile networks. Here we have a map of part of Aalborg. Here we observe base stations. These base stations have cells. A cell, for example this one, is serving a number of pixels. So these squares are pixels. They have traffic demands, and cells provide with coverage. Cells can be turned on or off. A power saving schedule is an hourly based plan for turning on off cells. There are some requirements. For example, they should preserve the coverage, and they should be energy optimal, and there are some other quality indicators which are relevant. Our goal in this project is to automatically synthesize near optimal power saving schedules which satisfy the requirements. What is really nice about this project is that we are cooperating with the company to operate, which has provided data. We have a database quite big with a lot of tables, and from this data we are able to recover relevant information useful for our simulations, containing information about base stations, cells, pixels, etc. Here we see in detail a number of pixel information from the map we have seen before. We see that pixels have some geographical coordinates, and pixels have a number of cells like this with a frequency 800 or 1800, and there could be several cells associated to a pixel. Now, given all this information and data from the company, what we do is the following. We are building a simulator that is going to simulate the traffic, how the cells are turned on and off, and their effect on the pixels. So for this we build this simulator in Python. The simulator is connecting directly to the to operate database, and it works as follows. At every hour, the simulator is going to collect the status of the network, and it's going to send this information to a controller. For example, a controller could be Upal Stratego. Then the controller replies with a control strategy. And this control strategy is basically a power saving schedule. More concretely, in our simulator we have a game, a stochastic game. It's stochastic because the traffic could have some stochastic or can be modeled using probabilities. Our controller, Upal Stratego, has also a model, but this one is a more abstract model, and it is going to compute a strategy or a scheduler for a very short horizon, but it uses the same number of cells and pixels. So we have a simulator implemented in Python. Basically, the simulator, what it can do is can turn on and off cells. If a cell is turned off, then the contribution that this cell makes to a pixel is going to be 0. It has some traffic loads. So currently the simulator is replaying historical data. So it looks in the database for what is the traffic associated to a cell, and then is distributing the traffic of the cells uniformly to the pixels. briefly, Upal Stratego, which is the tool that we are using to compute the strategies, is a tool developed at the DICE unit at Aalborg University. It uses simulation-based statistical machine learning methods to compute strategies. More formally, what we are doing is the following. So, if we are given a strategy, sigma, for a horizon, it could be, for example, 1 month, then the game or the network restricted to the strategy becomes a stochastic process. What this means is that we can now take the expected value of some variable, for example, the reward. And what we are after is to find a strategy that is going to minimize this reward. In our concrete scenario, the reward is the following. It accumulates a penalty and an energy at a given point in time. So energy is defined as follows. So we consider the number of cells that we have in the system right now, and if the cell is on, then the energy is the power that it costs to operate the cell plus some cost per megabyte. Otherwise, the energy is 0 if the cell is off. And the penalty is as follows. The penalty is 0 if for every pixel the contribution is positive compared to the demand. If this is not the case, so the pixel, the coverage is not good, then we penalize with a high value. And we are working with very big scenarios, and basically we need two technologies to be able to manage these big scenarios. The first one is called online synthesis. So ideally, what we would like is to control a network which has a number of cells n for a very large horizon h. This h could be, for example, 1 month. So ideally, we would like to compute this strategy for 1 month. Since this is very big and we have to make decisions at every hour, it's not possible to compute such a strategy. So what we do instead is we compute a very a short time horizon strategy for the next 3 hours. So when we start the system, for example, we have all the cells on, and then we have 1 hour to compute a strategy. Then in the next controlling point, we use the strategy that we have computed, and we start computing the new strategy, the next strategy. Note that these strategies look only for a short horizon. And we keep doing this until we reach the big horizon. By doing this, then we need to consider way less decisions. So if we have n cells and we have only 3 hours, then for 1 month we will only need to, at every time we need to compute a small strategy, we need to look to 2 to the power of 3 times n decisions. Instead, if we were going to compute this big strategy, then we would need to look at this big number of decisions. But still, now we have this number that is more tractable, but still we have a lot number of cells. Still cells are, so if we have a scenario where we have 20 cells, we will have this number of decisions, and this is still too big. So in order to deal with this complexity, what we do is we have a distributed controller. So basically, we are grouping cells in groups of 8, and we create a partition of the word. So for example, we could have like a controller for this part, then another controller for this part, another controller like this, and another controller. Then we are gonna create a model for every one of these partitions, and we are gonna synthesize the near optimal strategy for every partition, and then we are gonna merge them together. This is how a UPAL model looks. We have here these solid edges. These edges constitute the controllable actions. So this is what we can control, and the dashed edges are the environment. So we see here that the controller can set on or off the cells. So it's gonna set on and off the number of cells that is controlling. Then it's gonna evolve the system and computing a reward, and it's gonna do this for a short horizon. When it finishes, after doing a number of simulations and some machine learning techniques, it's going to return the optimal, near optimal actions to take. We have carried out a small experimental evaluation. Small in the sense that we only consider 2 scenarios. We have CitySuit, which has 39 cells, and Friedendal, which has 107 cells. We are considering 2 controllers. The controller all on, in which all cells are always on, and the UPAL Stratego controller. We are looking for a horizon of 1 month. In this table, we have some results. For CitySuit, the all-on controller, which is not optimizing any reward, uses this amount of energy, 3,473, and the reward is 150 million, about 150 million. Of course, this controller is not optimizing for the reward, it's just to have a baseline. UPAL Stratego is optimizing for the reward, so we have a smaller value, 141, and this is also reflected in the energy usage, so it uses 3,191 energy units. In the bigger scenario, when all cells are on, this is the usage of energy, 10,115, where by using UPAL Stratego, it uses 9,300, so it's about a 10% energy savings in 1 month. So we have implemented a simulator that is quite flexible. However, there are many things we would like to do. So we have these distributed controllers, but they do not cooperate. They don't share information between each other. We would like to have a cooperative approach. We would also like to compare to operate the schedulers, so have more real controllers and simulations. We would also like to identify interesting scenarios. So we have just by random 2 scenarios, CitySuit and Neurotranders, but we would like to consider maybe events like when there is a stadium in a game. We would like to evaluate what could be done there. We could also refine our models and the reward. We could include more quality measurements. And we also would like to develop better traffic load models. So currently we are using historical data, but we would like to use a forecasting of how the traffic develops. And with this, I finish this presentation, and I thank you for your attention.